It's my great pleasure to introduce Kalesha Bullard, who is a postdoctoral researcher at Facebook AI Research. She completed her PhD in computer science at Georgia Tech in 2019. Her research during the PhD was focused on in the space of interactive robot learning. Now, during her postdoc, she has expanded her research to explore the space of multi-agent reinforcement learning, investigating how to enable embodied multi-agent populations to learn general communication protocols. During the last year, Kalesha was selected as one of the 2020 Electrical Engineering and Computer Science Rising Stars. She has also participated in a number of service roles throughout her research career, including service for organizing and program committees for workshops associated with several top artificial intelligence conferences, such as NeurIPS, AAAI, AAAI, AAMAS. Today, she is going to be telling us about learning through interaction in cooperative multi-agent systems. So, Kalesha, the floor is yours.
Thank you, Maziar, for introducing me, and thank you for inviting me to virtually visit you all and share with you all what I've been working on. So a key theme of my work has been on learning through interaction within multi-agent systems that are cooperative in nature. And the overall aim is for AI agents that can learn and coexist with other agents like the ones you see in the pictures in their shared environment. So today I'll share a selection of my work in this general space and discuss the exciting progress that we've made thus far. So multi-agent systems are pervasive in biology. Being part of a multi-agent system is useful for food, like the deer on the bottom middle, for safety and survival, like the hyenas on the left, on the bottom left, but also seemingly important for companionship, like the gorillas at the top right, or social learning, which is part of how humans acquire part of their skill set. So you see humans on the bottom right learning through social learning. Multi-agent systems are also pervasive using technology. A diverse set of multi-agent systems are beginning to be used both in the real world and in people's homes, like in the images you see above. So you see a self-driving car in the top left, a factory setting with robot arms and humans in the top middle. Traffic light system, even though you may not think about it, is also a multi-agent system where you have multiple artificial agents because they have computer chips that can interact with one another. And then on the bottom right, you see this more futuristic human robot. We have not realized this vision yet, but this is something that we're moving towards. So these images show the heterogeneous nature of multi-agent systems, including both multiple artificial agents and humans coexisting in shared environments. And my research broadly takes inspiration from these types of problem settings. So my overarching research objective is to investigate principled methods for learning through interaction in environments where AI agents coexist and aim to achieve shared goals with other agents, whether human or artificial, and similar to the pictures or the images that we just saw in the previous slide. So my research vision really involves the use of interactive learning methods, and that can be through human agent learning or multi-agent learning, towards this longer term goal of cooperative multi-agent systems. And as you see in the image here, you have artificial agents and human agents. And this is because as we get towards more realistic settings, which is what I take inspiration from, artificial agents will have to coexist with both other artificial agents and human agents. So the multi-agent systems that we aim to put them in as we go towards general intelligence are very heterogeneous in nature, and the artificial agents should be prepared for that. But one intermediate goal is for multi-agent systems to include only artificial agents. And an important consideration here is that even as we study fully artificial multi-agent systems, we can also include simulated humans as part of the population in order to get us closer to our long-term goal of heterogeneous multi-agent populations and coordination. So I've been talking about learning through interaction as part of the title of my talk. So, I want to talk a little bit more about this family of methods. And I think there are three dimensions, at least three dimensions along which one can perturb the interactive learning problem setting. So the first has to do with who initiates the learning, passive versus active. In the passive case, the teacher will initiate the learning with the learner by providing guidance. In the active case, the learner, which typically is, in my work, the artificial agent will be the learner, and it is actively soliciting feedback through querying the teacher. The second axis is what type of input is provided through the interaction, supervision versus reinforcement. And I should say that all of these can be fluid, so you can do combinations of these, and there are different variants of them. But supervision really focuses on instructive feedback. So if you have, really about correction and error signal. So if you have an agent that performs a task and it doesn't do well, a supervisory approach would be to give it instruction in terms of what it should do differently in order to improve its performance and how to improve its behavior. Versus reinforcement is really an evaluative signal. It's quantitative in nature, and it's more about how well the agent did. So it doesn't tell the agent what it needs to do differently in order to solve the task correctly or in order to improve its behavior. That is called the credit assignment problem, where the agent has to figure out where to assign credit or blame for its performance. And this is a problem that the agent has to solve for itself in reinforcement learning. So it adds to the challenge. The third axis is who provides the input. And you can imagine this coming out of the page. And it's really about who's actually playing the role of the teacher. So it can be the human agent, and in the domains that we'll talk about, we basically assume that the human agent is like the expert. So the human would have given the task and they have expertise about it. So it's more like a teacher in a classroom versus other artificial agents. And, in the domains we'll talk about, the other artificial agents are novices. So they're co-learning with the learner. And it's more like students in a classroom that are engaging in cooperative learning. So my PhD work started with passive learning from demonstration, where a human teacher would provide examples or feature information to a robot learner, and the learner would be a passive observer of the data that it was getting from the human. In the second part of my thesis, or the latter half of my thesis work, my PhD work, I was really interested in the learner starting to take more ownership of its learning process and starting to manage its own learning interaction by actively querying the teacher whenever it wanted to resolve its uncertainty. And so that's this focus on active learning. And then in my postdoc, I started to think more about, or I became more interested in, what if we don't always want to have a dependence on having a human in the loop, and we can leverage the opportunity to learn from other artificial agents who are co-learning, other novices that are co-learning. And so this really propelled me into the space of multi-agent reinforcement learning, which is what I focused my postdoc on. So this talk will focus on the top two. In particular, I'll spend most of the time on the multi-agent reinforcement learning, but I also talk some about the active learning work. And the passive learning work, I'm happy to talk about offline if someone has more questions. Before we dive into the projects, though, I want to talk about the computational frameworks for reasoning that I've used in both of the interactive learning projects and how it's been modified for each. So it is the case that I always use decision theory in my work, is always using decision theoretic computational frameworks for reasoning. So in the first kind of decision theoretic framework, it's for learning through human agent interaction for active learning. The active learner is this Black learning agent I. It can take observations from the world, and it can take action in order to change the state of the world. Now, this particular paradigm was really intended for a robotic agent interacting with a human agent as a teacher. So the world itself was considered to be physical world, which is non-stationary. It's changing over time, as you'd expect in physical environments. And the human teacher, we expect their model to be stationary because they're an expert who's already acquired this knowledge a priori. And so the agent is not necessarily changing the human's model. That's the assumption. So we modified the decision theoretic framework in a few notable ways to think about the problem of multi-agent reinforcement learning. So here now you have two agents that are learning in parallel. First of all, the Black learning agent I can take reward from the environment as well as observations. And the other learning agent, we assume that their model or their policy is non-stationary because they're also adapting over time to the learning agent. Now, we also simplify the environment. So this is a more abstract problem domain. We're no longer thinking about physical robots. So we assume a simulated stationary environment, but it's still challenging because from the perspective of the learning agent I, the world still seems non-stationary. And non-stationarity has the implication of the agent constantly having to update its learned model over time. So the other thing I want to say about this is that the active learning and reinforcement learning are set in different problem domains. And for active learning, it's really a planning-based regime where you have this utility function, which is an objective function, and it's a combination of several different individual objectives SPI, which have been manually designed by me, the researcher. And then in the reinforcement learning case, the agent is getting rewarded by experiences in its environment. Okay, so let's dive more into the projects. So the first part of the talk, which is going to be the shortest part actually, I'm going to talk about the active learning work to set the stage of information extraction from a human agent. And in this case, I will introduce the computational framework that we used for active learning and how we incorporate constraints of the teacher agent. So this is really a fundamental contribution for active learning for realistic human AI settings. And this is joint work with the collaborators that you see above that we did when I was at Georgia Tech, and actually all of us were at Georgia Tech at the same time. So we talk about realistic problem settings. So let's first start with the standard problem setting for active learning. So typically you have a static pool of unlabeled instances, U. From this, the learner will extract some set of candidate queries, X. Typically in active learning, the candidate queries are closed-ended queries. So for example, what class does this instance belong to? Or does this instance belong to this class? And the teacher would say yes or no. Is this feature relevant? Yes or no. Which of these two feature subsets is most relevant? And the teacher would select one, right? So it's a very limited communication action space. The learner will select an optimal query using some utility function, and then it updates both of its instance pools. The unlabeled pool, you subtract the query from that, and then the label pool gets a new training instance. This label pool is used as the training sample to update your classifiers, and then this repeats until termination. And typically the stopping criteria in active learning is depletion of the unlabeled pool U or depletion of the query budget that the learner has been given. So these red pieces are how we change the problem setting for more realistic human environments. So first of all, if you have a robot that coexists with a human and it's continually learning, it doesn't have some unlabeled pool of instances that's static. It has a dynamically changing environment, and it needs to use its sensors to extract scene information. The next thing is that the agent should be able to reason about the state of its learning, so its learning belief state, and use that to reason about the progress of its learning as well. We also want to take inspiration from human teaching and learning settings. And if you have a human learner, it's not limited to only closed-ended queries that are like yes or no responses. A human learner can ask open-ended queries. A human learner can choose to not query at all because it's not advantageous. So we really want to have a more expressive communication action space for our learner, just like we would expect in more realistic human learning settings. And then the final thing is that in a more realistic learning setting, there actually is another agent, which is a teaching agent in the shared environment. So the learner should be able to explicitly reason about how the teacher's constraints impact its action selection. All right, so that was those are some of the key things that we contribute. And before I move on, I do want to say this represents a fundamental contribution to the space of active learning for agents that coexist with human agents, which is not typically what the active learning problem is set for. So our problem here is going to be learning object concepts in a non-stationary environment for a robotic agent that's continually learning. And so we can define the learning problem as such. The agent needs to infer a mapping G that goes from the set of concepts or labels to some set of object instances in the environment that can ground those concepts. So here are some examples of the type of non-stationarity that we might expect in a physical environment. So the concepts Y1 through Yn are what the agent is trying to learn a model for using the grounded instances from its environment. And examples of non-stationarity might be orientation and lighting, like in the Y1 case. An underlying object state is changing, like if you were eating a pie, like in the Y2 case, or changes in texture, like when my cat scratches my couch. And this is like what the Y3 case shows you. It's also the case that here we assume there's no external data set. So the agent is getting all of its training information from querying the human, and it's given a query budget to represent the idea that it doesn't have unlimited access to the human. Okay, so the first thing that we contribute is a learning belief state, which we define as the learner's estimate of the conditional probability distribution of concepts Y given unlabeled instances X in the environment. Each PXY is the probability that instance X belongs to class Y. We also have this more expressive communication action space. So the black label query is your traditional active learning query, where the agent is asking for a label for an instance about which it has uncertainty. So it might say something like, is this object an example of a fruit? And the human would say yes or no. But we also add these open-ended queries. So asking, can you give me an example of a fruit? And the human can choose any instance in the environment. Or what features would you use to differentiate between fruits and beverages? And this is really kind of pre-deep learning era. So feature subset selection is really important, particularly if you want sample efficient learning. And then the agent could choose to not query because it's not advantageous. So this really gets closer to what we might take inspiration from in a human teaching and learning setting, a more expressive set of actions. And one of the key challenges here was to give the agent a response space for the teacher that made it a feasible learning problem. Particularly when you ask open-ended questions, you need to consider only a feasible set of responses that the teacher could give. And so as typical in decision theory, you select the argmax action based upon maximizing expected utility. And the objective function in this first iteration of the work takes into account, similar to other active learning approaches, takes into account learning objectives or learning progress. I'm not going to go into details about that, but suffice it to say that all were pertaining to statistical metrics on this learning belief state, and they were designed to be task agnostic, so sufficiently general for a broad range of classification-based active learning tasks. In the second iteration of the work, we really wanted to expand the decision function, so the expressivity of the decision-making capabilities, to consider not only the agent's learning objectives, but the teaching agent, the constraints of the teaching agent in particular. So the idea is that it should maximally leverage the teaching time and cognitive resources of the human. So basically trading off not only learning objectives, but wise resource consumption, where the teacher is the key resource. And so it's reasoning about the time and cognitive load, or proxies for time and cognitive load of the teacher. And we actually use imitation learning to figure out how to trade off such a diverse set of decision criteria. All right, so these green things represent the key contributions of the computational framework for active learning. So let's talk about a little bit about one key experimental result. So in our experiments, we explore non-stationarity within more realistic environments. So these are examples of non-stationarity you might see, like if the agent needed to prepare lunch, the pasta might go from being in a box to in a pot to being in a bowl when it's being served. And we also want to vary the rate of environmental change to see if the agent can adapt to non-stationarity in the environment. So this is how we do this. So here's one result for how we do this. So the gray vertical lines represent when environmental change occurs. On the left side, it's more gradually every 20 time steps. On the right side, it's more rapidly every time step. The dots represent when the active learner chooses to make a query, and the accuracy on the test set after it makes the query. The green line represents when all the baseline active learners deplete their query budget, which is a 60 query budget. And they do it after 60 queries because they assume it's always advantageous to make a query and learn a sample as efficiently as possible. And then the orange line represents when our experimental approach depleted its query budget. So you can see that it's able to spread the query budget out over time on the left in the gradually changing environment. And on the right, in the rapidly changing environment, it increases the frequency of its querying to adapt to the non-stationarity within the environment. So consistently in both sides, on both gradually and rapidly changing, the learner is able to observe a very diverse set of environmental states. So it sees a lot of different environmental states. So it sees a lot of environmental change, and thus acquires a more representative training sample no matter how quickly the environment is changing. So it's able to adapt to non-stationarity within the environment. And this was really an exciting result, actually, particularly for continual learning for a robotic agent. So the key finding is that the decision theoretic learner that we propose consistently makes effective use of its limited query budget by requesting information primarily when change occurs in the environment. Okay, so this is a video illustrating just a manual. I hand-coded a demonstration of what the teaching learning interaction might look like if you actually had it online, but this is not online, this is hand-coded. So you might ask, okay, so you had some exciting results, which I only talked about one, but there were some other exciting results. So what were some of the reasons why you switched to reinforcement learning, for example? What are some of the key limitations? And so this has to do with, with active learning in general. One of the things is it's a planning-based regime for reasoning. So as the researcher, I had to manually design the objective function. And certainly I manually designed it to be as general as possible for an entire class of tasks, but also as effective as possible for each individual task. But it felt much more like an effort in human ingenuity. And really what I'd like to see is the agent being able to learn a policy. And so this really moves us more into reinforcement learning, a learning-based regime for reasoning. The other thing, a second thing is that sometimes it's really advantageous to have a human in the loop, and that's actually what you want. But oftentimes you don't need to have a human in the loop, and then we can circumvent some of the constraints that come along with having to depend on humans to give us data. And then a third thing that's important is that the active learning problem is typically assumed to be myopic, which means the learner only reasons about one time step out. And there's some good reasons why, because it's really computationally inefficient. And so we want to kind of account for this. But I was really interested in exploring sequential decision problems where the learner can reason about the long-term consequences of its decisions. So again, this really takes us to this paradigm of like reinforcement learning. But on a more personal level, the other thing is, I remember two distinct conversations from my PhD with my advisor. The first one was, can we abstract away the robot? Okay. The second one was later my PhD. I was like, can we abstract away the human? One of those I got away with, the other one I didn't. But basically, what I was most excited about this work was not the human or the robot specifically, but the idea of an AI agent that could reason in meaningful ways about other agents in its environment, and in particular, leverage interaction with those other agents to acquire what it needs. So really about modeling and reasoning about other agents and learning, social learning with other agents. This video was made at the end of my PhD. I saw my postdoc as an opportunity to delve further into questions that most fascinated me, which were really around multi-agent reasoning and learning. So now we go from human agent active learning to multi-agent reinforcement learning. So first I want to motivate this entire section. Imagine you had all these embodied agents operating in this shared autonomous vehicle ecosystem. And you want them to learn to communicate to aid in coordination. So coordination is a really more historically multi-agent kind of task. We're diving into a more historical kind of multi-agent task, and you want them to learn to communicate. So one question is, how about you just do supervised learning from data sets or imitation learning from demonstrations? But a challenge is that supervised learning requires huge existing data sets for each of the agent embodiments. So if you had different types of cars, you might need a data set for each of the artificial agents, each of the car agents. Multi-agent reinforcement learning provides an opportunity to allow agents to learn communication solely through agent-agent interactions. So you can turn compute into data. And it allows a flexible adaptation of your communication protocol in case something arises, like the huge power outage that happened in Texas, and maybe you now need to change your protocol. Agents can do it in accordance with the setting that they exist in through agent-agent interactions. So we want to use multi-agent reinforcement learning to learn our communication protocols as opposed to supervised learning. So now this takes us to the second part of the talk. So the last part, we're talking about information extraction from human agents. Now we're going to talk about communication of information with other artificial agents. And so I'm going to introduce this framework for zero-shot communication, how we induce bias in order to realize zero-shot communication, and then how we scale up to more complex domains, and then open challenges. And so this work is joint work with the collaborators that you see above that are also at FAIR. And it's really about multi-agent reinforcement learning for zero-shot communication. And some of this work is currently under submission. So even though I'm moving into this more abstract space, I still take inspiration from my prior work in embodied domains. And so the question is, how can we emerge general communication skills for embodied agents through motion, right? And it's motivated by the idea that embodied agents such as humans and robots inherently communicate through movement. And if we want to move towards human level intelligence, which is an embodied type of intelligence, we need to enable our artificial embodied agents to also communicate through this more realistic channel. So first, let's talk about the learning problem. What does it mean to learn a communication protocol? So let's say you have 3 agents, a blue, orange, and a green, and they're given some set of reference ahead of time, and reference or communicative goals like hi or yes or turn right, so abstract communicative goals. The underlying idea is that each agent in the population must learn to generate a message for every referent in the library that it's been given a priority. The learning problem then is for every agent to learn a policy mapping the set of reference to the message space. And so a concrete example is, let's say the reference or communicative goal is hi, and the message would be a wave. Okay, so referential games are a type of multi-agent signaling game that have been used extensively in the multi-agent communication literature for communication protocol learning. The premise of the game is as follows. And so from here on out, I'm not going to say reference, I'm going to just talk about communicative goals as the kind of referent that we are learning in this work. So sender agent Alice is given a communicative goal G. She needs to generate a message M for the receiver agent to observe, and Bob needs to infer what communicative goal Alice is signaling to him with that message. And then the loss is the distance between the true communicative goal and the predicted communicative goal by Bob. 2 important assumptions persist in the typical protocol learning problem setting. The first is that it's a discrete communication channel, which means a message is an individual action that comes from a set of discrete actions. The second is the assumption of cheap talk, which means that communicating a message has no cost to it. It's completely cheap. But these are 2 challenges when we talk about embodied agents. And I'll tell you why in a second. But this is basically a sample of prior work from multi-agent communication literature. It's not intended to be exhaustive, but just to briefly illustrate where prior literature has focused. And a key limitation of prior work for embodied agents is the 2 assumptions I just talked about. Because if we want to talk about implicit communication through motion, number 1, that's not a discrete channel. Motion is going to happen through a continuous channel. If you have several degrees of freedom, it's a high dimensional continuous channel. And the other thing is that it's not cheap to move. You actually have to exert energy, so it's costly communication. So we're going to relax each one of these assumptions one by one, starting with the assumption of cheap talk. Okay, so I'm going to define some parameters of our problem setting. First, some assumptions. We assume a fully cooperative setting. We assume that the communicative goals are given to the entire population of agents a priori. And we assume the protocol emerges solely through agent-agent interactions. There's no data or supervision. We formalize this problem as a multi-agent, decentralized, partially observable Markov decision process, which is a mouthful, so a DEC-POM-DP. And I'm going to just go over some of the properties of the DEC-POM-DP that are relevant for this talk. DEC-POM-DPs have N agents in general. For the signaling game, there's 2. Each agent has a set of private observations that other agents cannot see. There's a set of actions. In our game, it's a communicative game only, so all of the actions are communicative actions only. There's a set of communicative goals, which DEC-POM-DPs typically don't have a set of goals. So you can think about this as a goal condition DEC-POM-DP, but it's necessary for our game. And then the shared return for all agents are, because it's fully cooperative, it's a shared return. Okay, so we also are going to set this in the problem setting of Zeroshot Coordination, which was introduced last year at ICML, which is the International Conference for Machine Learning. Zeroshot Coordination is a setting where agents coordinate at test time with other agents who've been independently trained. In other words, novel partners, agents they've never seen, they've never had the opportunity to influence, they have to coordinate with at test time. So this prior work introduces equivalence mappings of policies, which are bijective mappings, and we're going to build upon this idea of equivalence mappings. So I'll talk about this more as the work goes on. And in particular, they formalize symmetries for the underlying DEC-POM-DP, symmetries for the transition model, symmetries for the reward function, and symmetries for the observation space. So we're going to build upon this idea of symmetries and equivalence mappings for multi-agent communication. So we introduced a novel problem setting of Zeroshot Communication, which is an instance of the Zeroshot Coordination problem setting, where the coordination goal is to learn a communication protocol that effectively generalizes to unseen agents. So let me talk a little bit about what that means. So let's say you have agents training in Selfplay. So this is a very typical training regime for multi-agent communications. Agents train in Selfplay. What is Selfplay? So here you have 2 different pairs of Selfplay agents. Let's look at the green. So let's call the sender agent always pi1. And pi1 is going to take in the true communicative goal G and a private observation O1. And it can take an action, which is the message A. Let's call our receiver agent always pi2. Our receiver agent pi2 can take in the action by the sender, which is the message. It can take its own private observation O2, and then it produces G hat, which is its prediction of the communicative goal. And then the return, the shared return, is the distance between the true communicative goal by the sender and the predicted goal by the receiver. Okay, so here we have two different pairs of self-play, and self-play is a bit of a misnomer because they're really two different agents, but basically they have the same ID, so they're like self. So cross-play is effectively, we want to cross the agent pairs. So now every sender will see every receiver that it never trained with, right? Unseen agents that were independently trained. So blue sender gets paired with green receiver and vice versa. And this is what we use cross-play for. So to be fair, in multi-agent learning, you can actually train in cross-play as well, but we don't do that. We're actually using cross-play for testing, for evaluation. This is how we test zero-shot communication, because now you have agents that are tested with agents they had 0 shots to train with, and you want to see how well they communicate at test time with these novel partners. Okay, so what's the problem with training using self-play? Because that's a perfectly reasonable regime. What's the problem with training using self-play if you want zero-shot communication? Let me be a bit more precise. So the problem is that if you just train using self-play, you're going to have agents that co-adapt to their training partners. So across different training pairs, you have many equivalent but incompatible protocols. So to be a bit more precise, this is representative of the optimization landscape. Let's say each of these red dots is a different protocol that a pair of self-play agents can converge upon. In order to have zero-shot coordination, you need them to agree on the same protocol, which means converging on the same optimum. So let's say one of these protocols is an English protocol, another is a German protocol, another is a French protocol. 3 different sender-receiver pairs converge on 3 different protocols, which are all equivalent but incompatible. So they're all perfectly reasonable protocols to converge upon. The problem, though, is if you want zero-shot communication, now let's say you pair a German sender with an English receiver, there's no reason to believe that these agents are going to be able to coordinate zero-shot because they converged on different protocols. There was nothing to incentivize them to converge on the same protocol, given that they couldn't pre-coordinate. So what we want for zero-shot communication is to change the optimization landscape such that you have one globally optimal protocol. So all individual agent pairs, all pairs that are trained independently, are incentivized to converge on the same global optimum, which is maybe, let's say, a German protocol. So now you have a German sender and a German receiver who never saw each other at training time, but you can still expect much better test coordination success because they converged on the same protocol. Okay, so how do we do this? Our general approach is that we first induce bias with priors on the solution space, but we don't want to just have arbitrary priors. We want priors that come from real world constraints, the kinds of realistic environments that these agents might exist in. And then we want to use that to engender a globally optimal, unique protocol. But in addition to that, we're going to adapt the learning objective to select better global optima by exploiting equivalence classes of communication actions. And I'll talk a bit more about this. So these are 2 different ways that we're going to basically change the learning objective. All right, so the first is inducing bias from priors from the real world. So when you have embodied agents like the self-driving car or robot arm, it's not cheap to communicate. In fact, it requires energy. They have to exert energy. So communication is costly. So we want to exploit this. The other thing is that in a more realistic setting, what you'd expect is that all communicative intents don't occur with the same frequency. So you'd expect yes or no to occur with higher frequency than turn right. So we want to exploit that as well. When you put these 2 together, what this incentivizes is a minimal effort protocol. Why? Because what happens is the most frequently occurring intents should get paired with the least costly or least energy exerting actions. So you want to incentivize the agents to learn a communication protocol where they minimize the energy over the course of the protocol. So there's an inverse relationship between how frequently an intent occurs and how much energy that intent should exert, right? But this picture gives the idea that there should be one globally optimal minimal effort protocol. Is that always true though? What about when you have symmetries in realistic communication, which occurs a lot in fact? So I'm going to give you an example of a symmetry. Let's say we have some communicator go high. There are 3 different equivalent ways, so they all exert the same amount of energy, but different ways to say hi. One is a wave of my left hand, another is a wave of my right hand, and another is a nod. So let's say all those exert 1 unit of energy. That means if my communication protocol only has this one intent, there are 3 different equivalent ways to learn a protocol, right? So these are all, so each of these protocols are equivalent but incompatible because they all have the same communicative goal but different actions. So if I'm a receiver and let's say the sender I trained with waves with its left hand to say hi, but now I see a new sender at test time that nods, I'm not going to be able to recognize what it's communicating to me because I learned a different protocol. Equivalent but incompatible. So how does symmetry impact the optimization problem? Well, when you have no symmetry, so no redundancy, it does look like that picture I showed you before. There should only be one unique minimal effort protocol. There's only one way, in this case, to map the set of goals to actions according to energy exertion. But if you have symmetry, which means redundancy in your action or your goal space, so now I have multiple actions that exert the same amount of energy, i.e. they have the same cost, they're interchangeable. So there are different ways to learn a minimal effort protocol, which means that I have multimodality in the optimization space now. So I reintroduced the idea of having multiple equivalent global optima. In this work, we're going to focus only on action symmetry, but you should know that if you have goals that have the same likelihood, this will again induce multimodality in the optimization space. And you could also relax that assumption. That's something that we actually want to do in future work. All right, so let's talk about what this looks like for our protocols. So here we have 2 pairs of self-play agents, an orange pair and a green pair. Okay, so on the left, we have the sender policy. The sender policy, the y-axis shows you what the sender takes as input. It takes intents. So there are 5 different intents that the sender can take as input in this example. The x-axis shows you the output. So the sender can choose one of several different actions to assign to each one of these intents. The middle column shows you the receiver policy, a visualization of the receiver policy. So the x-axis again is the receiver's input. So the receiver can observe one of several different actions taken by the sender. The x-axis is the receiver's output space. So it can predict one of several different intents based upon the action it observes from the sender. And then the right column is the confusion matrix. So this shows agreement between the true intent by the sender and the predicted intent by the receiver. What you want to see is the diagonal has the most probability mass because that means there's an agreement between what the sender intended and what the receiver predicted. So here what you see, the key thing that I want you to see here is these are 2 equivalent but incompatible minimal effort protocols. So intent 0 is the one that occurs with the highest frequency. It gets mapped to action 0, which has the lowest energy, right? There's only one way to assign intent 0. However, intents 1 through 4, which all have different amounts which all occur with different frequencies in that order, can get mapped to any of the actions 1 through 4, and you still have minimal effort. So you can permute these different actions and assign them to each of these 4 intents, and you still have a minimal effort protocol. So in self-play, each of these agents perform well with their training partner. So there's high self-play training coordination. With almost 96% accuracy, the receiver is able to predict what the sender is communicating. But what happens in crossplay? Now, when you pair the orange sender with the green receiver, or vice versa, it turns out they're not able to communicate that well because, again, I'm going to keep repeating it, equivalent but incompatible policies. So now in crossplay, it turns out that they do very poorly with respect to zero-shot coordination. The receiver is not able to predict what the sender is communicating to it. So the question is, how do we address this gap in communication efficacy between training partners and novel partners? So our approach is to actually adapt the learning objective for the communication protocol learning problem. So here's your typical self-play learning objective. In self-play, the receiver agent Pi2 is incentivized to optimize for an individual sender, Pi1, which is its training partner. So you want to jointly optimize for the protocol that maximizes their interaction. But other play was introduced last year. This is also the same work that introduced Zeroshot Coordination. It was introduced at ICML last year. They actually changed the self-play learning objective such that now Pi2 is incentivized to optimize for an entire equivalence class over policies Pi1. So now instead of the receiver agent only optimizing for the one sender is training with Pi1, it optimizes for any symmetry equivalent sender that it could see at test time to make it more robust to its test partner. So what this means for our communication problem is that we want to jointly optimize for an individual goal and an entire equivalence class over actions that could be used to communicate that goal. But I have this question for you. What exactly is the optimization function optimizing for? Okay, so let's do a bit of a deep dive into the optimization function. Because if we adapt the optimization function, it's helpful to know what it's actually doing. Right? So I'm going to dive a bit into the mathematical intuition behind the objective function. If you're less familiar with this domain or less interested in the mathematical intuition, that's fine. I will summarize at the end intuitively what it's telling us. But I'm going to claim for you that it's going to try to trade off two different things: maximizing information and minimizing cost. So we're going to start with, so I'm just highlighting J, right, the objective function. So P, it represents the true distribution, and then pi will represent some predicted distribution by the policy. So cross entropy, H sub P of Pi2 is typically, is a very typical loss function that you would use for multi-class classification. So we employ cross entropy for the set of goals. So you want to minimize cross entropy, which is really trying to minimize the distance between the true distribution P and the predicted distribution pi. And then we also want to minimize cost of the actions taken by Pi1. So green will be me expanding from the previous line to the new line. So cross entropy is expanded as such. What effectively is happening is that you're taking the log likelihood of the estimated probability of G from Pi2, and you're weighting that by the true probability of G from the true distribution. So now we're going to expand this out. So in order to predict G, the goal, it's always going to be dependent upon some action being taken by the sender from Pi1. And in particular, since we're employing the other play learning objective, it's going to be dependent upon an equivalence class over actions taken by the sender. Pi1 gets expanded. Pi1, remember, is the receiver policy. It is trying to predict some distribution over actions given the true goal. So this is how we expand each of these terms. So here's one of the key steps. Cross entropy loss is minimized when the predicted distribution actually matches the true distribution. So over the course of training, the Pi2 is moving closer to P. That is how cross entropy loss gets minimized. So we can expect over the course of training, Pi2 will approach P. This means that in the limit, we can replace P with Pi2, and we can say that we can weight the log likelihood given by Pi2 by the probability by Pi2. What does this give us? Well, when you have Pi2 log Pi2, you get back the entropy. So now effectively what this is doing is saying what we're effectively trying to do is minimize the conditional entropy using this estimated distribution pi of the set of goals given the equivalence classes of the actions. And it can be easily shown that when you minimize entropy, what you're effectively doing is maximizing mutual information between the goals and the equivalence class over actions. And so what does that really mean? That means we want to maximize mutual information, not just between goals and individual actions taken by our training sender, but goals and entire equivalence classes over actions taken by any sender, any reasonable sender that we could see at test time. Right? So hopefully this is trying to help us to better generalize to novel partners. And then the question is, in other play, which is the learning objective that we use to modify our learning objective, they actually assume that equivalence classes are given, but that's a limiting assumption in practice. So how can we obtain these equivalence classes? So we are going to propose a learning algorithm for that. So here's a key imitation of other play, which is what we use to modify our learning objective, but we want to now propose a learning algorithm that will automatically discover these symmetries. So the first step is to train a set of optimal self-play policies. And then for each iteration until convergence, the key step is that we want to extract symmetric actions across these optimal policies. So it's important that the policies are optimal. Here's the intuition behind the key step. Let's say you have some communicative goal G, and you have two different optimal sender agents that employ two different actions to communicate G. So one, G is high, one employs a wave, the other employs a wave with a different hand or a nod. What we can infer from that is these two actions are equivalent ways of communicating the same goal because the two senders are optimal agents. So they're going to do an optimal thing, which means we can infer that these two actions belong to the same equivalence class. And so this is the key intuition. It's actually quite straightforward, but it's also powerful because it allows us to now take these equivalence classes and use them to optimize or to learn a set of optimal other play policies. And one of the other cool things about QED is that it's a bit more general than other play because you're not just limited to symmetry in the very strict mathematical sense for a DECT POM GP, you can infer symmetry based upon optimal agents. And so even if the actions are approximately equivalent, which is where you get quasi from, you can still infer that they can be used in an equivalent way, they're interchangeable, so we can put them in the same equivalence class. So recapping the last 10 slides, basically, method recap. Problem, we have multiple globally optimal protocols because in cheap talk, there's no bias over one protocol, so they can be equivalent but incompatible. And then symmetry also exacerbates this problem because it gives redundancy. So we formalize this Zeroshot communication setting and learn protocols that are, we have a preference for minimal effort protocols using biases from realistic settings, and then we infer action equivalence classes in order to train a unique zero-shot communication policy. So now let's revisit our task from before. What that looks like is instead of learning a mapping between intents and individual actions, we learn a mapping between intents and entire equivalence classes over actions. So now intent one is mapped to a distribution over all actions in energy class one, and so on and so forth. So the receiver agent will learn if I see any of the actions in equivalent or in energy class one, I can infer that intent one is being communicated. So there's only one unique way to map intents to equivalence classes. So now when we compare self-play, so here are 5 different self-play sender receiver pairs that are optimal. And you see their self-play performance is very good, but their cross-play performance not so great. But when you compare this, here are 5 different optimal QED trained agents, and there's only one unique optimal. So it turns out that the self-play and cross-play performance is basically the same for QED because when you cross agents that have the same policy, they still do well. Whereas in self-play, they're equivalent but incompatible. So when you cross them, they don't do so well paired against each other. The other thing that's important to note here, however, is when you map intents to entire equivalence classes over actions, you use much more of the action space, which means you're going to use a lot more costly actions. So there is a trade-off. You get better communication performance, but you also exert more energy. So QED does have higher energy costs on average. Okay. So now you may say, well, Kalesha, you talked about embodied agents, but embodied agents move through this continuous channel. What happens when you have a continuous channel? So now you have this, let's say this articulated agent like a robot. It's inspired by like a robot. It generates motion trajectories now as messages, not just one independent discrete action. So this completely changes the message space, actually. So this is highly underexplored in multi-agent communication literature. Actually, this is the first work we know of that's going to use articulated agents and like a high dimensional motion trajectory as a message. But this basically makes the message space intractably large. So to give you an example, we go from this one discrete action to, if I only have 5 time steps for the motion trajectory for this robot arm-looking agent, it's like 180 continuous values. So it's like 2 orders of magnitude more message space. This makes the message space much more complex and much more redundant. So this is ongoing work. So currently we still haven't figured out how to infer action equivalences, but we're looking at self-play with the induced bias. And the question is, can we get zero-shot communication in this continuous setting using self-play with the induced bias? And so we do a proof of concept task, which is really the simplest communication task we can think of with only 2 communicative goals. Actually, we've done some more complex ones too, but I'm just going to show you this one result. So the upshot is So here we have energy over time. So energy cost over time. So this top middle picture shows energy cost at the beginning of training all the way to the end of training. There's 2 communicative goals, 1 and 2. 1 occurs about 2/3 of the time, 2 occurs about 1/3 of the time. So 1 is a lot more frequently occurring, so it should use less energy. And you see, in terms of energy cost and x-axis, 1 is always to the left of 2. So it is using less energy. The Gaussians on the right show you the energy distribution at the very end of training, so at 10,000 at the bottom. So what we see is, it is the case that we have very low entropy over the set of goals given the energy cost of the trajectories. So if you look at just the cost on the x-axis of the Gaussians, what you see is, even if I never see the trajectory, just looking at the energy exertion, I can with very high accuracy tell you which intent is being communicated, which means there's very low entropy, very low uncertainty, because the Gaussians basically don't overlap. So I can predict which Gaussian you're telling me just by telling you the energy exertion. The other thing that's important here is the Gaussians are pushed all the way to the left. Right. So remember, the other part of our objective was to minimize energy. If the energy was not minimized, the Gaussians would be over to the right, which would mean you would have low entropy, but you would also have high energy. But since the Gaussians are pushed to the left, you have low entropy because they're completely separable, but you have also low energy. So they're pushed as left as possible. So this is a great result. It says that prediction of the communicative intent is possible with just energy of the message. And here's an example of visualization of the policy. However, there's always a caveat. The caveat is this is not quite the whole picture. It's not this simple. When you have a really high dimensional continuous trajectory, it turns out that currently it's not able to pick up on this energy latent feature on its own. So if we tell it about the energy latent feature, it can get almost perfect zero-shot communication, but with the high dimensional trajectory, it's not actually able to pick up on this. So it is still the case that there's this learning problem in terms of how do we learn this latent energy variable. Also, when you scale up to more communicative goals, like G equals 10 intents, performance degrades significantly, so it gets harder as the communication task gets more complex. So there's still some clear open challenges, but this is a really promising result that we can get zero-shot communication even with this really highly complex action space. So our goal is to merge communication protocols motivated by embodied agents, costly communication channels, high dimensional continuous channels. So we introduced zero-shot communication. We looked at using realistic priors and constraints, as well as action equivalence classes to induce bias. And then we looked at what happens when you scale up to continuous actions. And just to give you a little bit of future directions I'm thinking about, which I'm going to go through this pretty quickly. Basically, I'm motivated by this idea of interactive learning in the longer term for heterogeneous multi-agent systems, like what you might see in more realistic settings. And then strictly artificial populations are an intermediate goal along the way. So the future directions correspond with this. Continuing thinking about strictly artificial populations, evolving from artificial to human AI populations is another thread. And then what happens when you get into the thread of human AI populations, which is kind of a longer term goal. And so in this thread of strictly artificial populations, I'll highlight one interesting question is around, what if you augment the optimization process with self-supervision? So something like a learning curriculum. Now I have a teaching agent and a learning agent, and a teaching agent is scaffolding for the learning agent. So, maybe it only gives the communicative goals one by one. Effectively, what it's doing is trying to structure the optimization process for the learning agent in order to more robustly converge on an optimal protocol. What happens if you want to evolve the population over time? So I start with a strictly artificial population and I start inputting humans into the population. How are these new human agents socially influencing the existing artificial agents that already were in the population? So how's the protocol changing? How are the behaviors of the agents changing as you gradually introduce these new agents, these underrepresented agents, into a population where you already had highly represented artificial? So think about like the factory setting where you have a bunch of robots and you start putting humans in. How are humans changing the protocol? And then the final thread is really about, multi-human AI settings. So what if you have this, you start inputting humans, you can no longer assume full cooperation because humans have self-interest. So, I mean, you have to assume that even if humans want to be cooperative, there's going to be some self-interest. So you might start thinking about game theoretical analysis of what happens with self-interest and how do you emerge full cooperation when you have some agents who are incentivized to perhaps defect. And then this idea of human compatible protocols. I mean, you saw those trajectories, right? They were quite arbitrary. If you ever want agents to be in realistic human settings, they actually do need to communicate in a way that's compatible with humans. So this starts opening up questions of how do you optimally combine reinforcement learning with supervision, with data or some kind of supervisory signal to make the protocols more human compatible, more compatible with human expectations or human priors of behavior. Okay, great. So this is acknowledgments to my collaborators and other agents, human agents who have helped support the research. And effectively what I've talked about is human agent active learning for information extraction. And it's really in this continual learning setting where you have non-stationary environments and realistic human settings. And then I've talked about multi-agent reinforcement learning for the communication of information with other agents and really trying to get towards emerging general communication protocols in embodied settings. So with that, I'll take questions.